Dear students, I welcome you for the today's lecture related to the dynamic behavior of controllers. That is, the controllers are already studied. They are basically your proportional controller, proportional derivative controller, proportional integral controller, and proportional integral and derivative controllers. The four different types of controllers. Now coming to the dynamic behavior. We have already discussed the dynamic behavior, that is what will be the response for something change to the set value or to the load variable. So this is the response or the output of a controlled variable. What will be the output for a certain specific change, that is whether it's a first unit step change, a sinusoidal change, a ramp change, or an impulse change, whatever the change may be. But we are going to study its response, that is the dynamic behavior. Dynamic means that is going to change with respect to time. I am going to change. What will be my response? What will be my output? Basically, I am interested in controlling a specific entity. That can be a temperature, a pressure, a flow, or a concentration. So I am going to control this, either of this entity, that is a controlled variable, and understanding its behavior with respect to the time, understanding its behavior, understanding its output with respect to the time. So we are trying to study, this is for the first order control system, and then we will study the numericals associated with this dynamic behavior. This also incorporates the servo problem as well as the regulator mechanism problems. Now, servo problems, that is the study of variation of controlled variable with the set point. Controlled variable is your C and the set point is your R. So it is the variation of C upon R, that is the study of variation of controlled variable with respect to the set point R. Now, in this case, the change in the load variable, that is U, that is with respect to time, is 0. That is related to the servo mechanism problems. And second type of the problems, that is associated as a regulator mechanism problem, where it's the study of variation of control variable with the variation in the load variable. That means it's a C upon U, that is output upon the input. Input I am going to change, whether it's a load variable or whether it's a set point, but output is same, that is C, the controlled variable, and the calculations related to the offset. We have already studied the response of a controller with respect to the time. Now how this response you get, that we are going to study it mathematically. So these graphs we have already discussed as a response of a controller, that is a proportional controller, proportional derivative controller, proportional integral controller, and proportional integral and derivative controller. This is the deviation variable, and this is what the offset, the variation from the set point. So this is also the same graph. This incorporates the PD controller. So we are trying to analyze or understand the behavior of this graph by considering the mathematical aspects, that is the variation with respect to time, as well as we are trying to study the servo mechanism problem and the regulator mechanism problem. By looking at this figure, the offset that you can already calculate or can understand, that is the difference for the proportional controller and proportional derivative controller. You are getting the offset. Offset, that is the difference in the magnitude of the set point and the controlled variable. This is what is your controlled variable. This level is of a controlled variable and this is the level of a set point. For proportional controller and for proportional derivative controller, there is a offset, that is the control variable does not attain the value of the set point. However, when the integral action that is incorporated, the offset becomes 0 and the proportion, even though the oscillations are there in case of proportional integral controller, the derivative, it reduces the offset. So a basic block diagram associated with this controller: R is your set point, B is the measuring element, R minus B, that is going to give you the error, E error that is generated. This error is going to a controller. This controller develops or gives the signal of pressure as the output from a controller. Here incorporates the I to P converter in case of a controller, and in case of a measuring element, it's again analog to digital converter that can be there. Then this pressure that goes to the control valve. Control valve, it adjusts its manipulated variable. This manipulated variable that can be affected by the load variable, and it finally goes to the process. So C is your output or the control variable. So in a block diagram incorporating the transfer function, I can write GC for the transfer function of controller, GV the transfer function of a control valve, GP the transfer function of a process, and H is transfer function of a measuring element. So all these are my values. Now I have reduced the block diagram by eliminating the control valve and by eliminating the measuring element. This is for simplicity to study the response. So we have only incorporated the controller and the first order system. So this is the study related to the first order system with the controller, the 4 different types of controller, and the step change. That is what we are going to study in this chapter of dynamic behavior of the first order systems. Controller with controllers. That means a first order system and a controller that has been incorporated. Only the two things are incorporated. And we are trying to analyze the response for a input of a step change. So I am going to provide a step change, and for that I am going to study its response. The transfer function of a first order system, that is 1 upon 1 plus tau s, that is what GS, which is equal to 1 upon 1 plus tau s. In case of a step change, the RT, which is equal to the 1, RS, which is 1 upon S. And for a controller, that is for a proportional controller, GC of S, the transfer function of a controller, that is GC, is proportional to the KC gain, controller gain. Then transfer function of a controller with the integral action, which is equal to the Kc into bracket 1 plus 1 upon tau is. Then the transfer function of a controller with the derivative action, that is Kc into bracket 1 plus tau ds or TDS. Similarly, the transfer function for a proportional, integral and derivative action, your transfer function is Kc into bracket 1 plus tau ds plus 1 upon tau s. Now, first we are going to study the proportional controller in a servo mechanism control problem. So what is a servo mechanism control problem? That is a study servo mechanism control problem, that is a study relating the output C or the control variable and the input R. So this is CS upon RS, that is our servo mechanism problem. And we have already studied in the block diagram reduction what will be the transfer function for the servo mechanism control problems. That is the overall transfer function, that is incorporating both the systems, that is a controller as well as the first order control system. That means relating this C and R. This R and this C. So this is the C and R that is related to the servo mechanism problem. And its transfer function is the product of transfer functions between C and R upon 1 plus product of all transfer functions in the entire control loop. That is, in this case, there are two transfer functions in between C and R, and 1 upon the product of transfer functions between C and R upon 1 plus product of all transfer functions in entire control loop. So writing this in the transfer function form, that is the GS, which is equals to CS upon RS, which is equal to GC of S upon tau S plus 1. That is what? For the controller, GC of S, and for the first order system, that is 1 upon 1 plus tau S upon 1 plus GC of S upon tau S plus 1. That is the product of all transfer functions in the control system. 1 plus product of all transfer functions in a control system. So this can be reduced to GC of S upon GC of S plus tau S plus 1. Then we are considering this for the first proportional controller problem. We are considering this derivation for the proportional controller problem. So GC of S, which is equal to the Kc. So substituting GC of S as the Kc and simplifying that, you get the Cs upon Rs, which is equal to the Kc upon 1 plus Kc, that is being taken as the common, and 1 upon tau upon 1 plus Kc into the S plus 1, where this value of 1 upon Kc plus 1 plus Kc is represented as tau dash. This value is represented as the tau dash. So this simplifies to 1 upon tau dash S plus 1. And the remaining part Kc upon 1 plus Kc, that is same here also. Now the step change that has been incorporated for this, and we will try to analyze the output or the response for this step change of Rs. So RT, which is equal to 1, a unit step change that has been assumed. So Rs, which is equal to 1 upon S. So multiplying by this by 1 upon S, and then taking the inverse Laplace transform for this, you will get the Ct, that is the output or the response, which is equal to Kc upon 1 plus Kc into bracket 1 minus e raised to minus t upon tau, t dash or tau dash. So this is what is the response equation for first order system with servo mechanism problem. Then at infinite time or at a steady state condition, that means there is no change at with respect to the time, no change of certain entity with respect to time. So at steady state condition, t, that is t tending to infinity, so C infinity, that will become equals to Kc upon 1 plus Kc. This 1 minus e raised to minus t upon tau, that is going to be 1, 0. So 1 minus 0, that is nothing but the 1. So C infinity, that is Kc upon 1 plus Kc. And R infinity, that is equal to the 1. So offset, that is nothing but the R infinity minus the C infinity, that is the difference in the magnitude of the set point. R is your set point, so the difference in the magnitude of the set point and the controlled variable at steady state condition. Controlled variable at steady state condition. So the offset, that is R infinity minus C infinity, which is equal to 1 minus Kc upon 1 plus Kc. So therefore offset, that is equal to 1 upon 1 plus Kc. So this offset, this is the characteristics of a proportional controller. That is what we have observed in this figure. It's a for proportional controller, the offset that exists. Then by increasing the value of Kc, that is your controller gain decreases the value of offset. So as I am going to increase this value of a Kc, so this value of offset, that is going to be decreased. So that is by increasing the value of gain Kc of a controller decreases the value of offset. That is what, where I have to adjust or where I can accept the or tolerate the value of offset. Till that point I can increase the value of Kc. So controller can be adjusted in such a manner so that the system remains stable within the region, operating region. So this is how much offset that can be tolerated, that I have to, or a process engineer that has to decide this. So once this is decided, then I am going to decide this value of a Kc. So this is what is related to the proportional controller for a servo mechanism problem in the first order system with a unit step change. Now we are going to study it related to the proportional controller for a regulator problem. Now what is regulator problem that incorporates? It is the study of response controlled variable with a load variable. That is the regulator problem. It's a study of controlled variable with a load variable, that is C upon U. And while reduction of a block diagram, that is the transfer function for the overall system for Cs upon Us, which is equal to the product of transfer functions between C and U upon 1 plus product of all transfer functions in the entire control loop. That is for a regulator problem. So our first order system, that is 1 upon 1 plus tau s, and 1 upon product 1 plus product of all transfer functions in the control loop, that is 1 plus gc of s upon tau s plus 1. So this is our controller gc of s, and this is our process. Again, using the first order system, then simplifying it, taking the inverse Laplace transform, you will get the Ct, that is the output response, equals to 1 upon 1 plus Kc into bracket 1 minus e raised to minus t upon tau dash. This is the response equation for the first order system with a regulator problem. Now, at steady state condition, that is t tending to infinity, this value that will becomes 0, and c infinity that becomes 1 upon 1 plus kc. So r infinity, that is what will be there, because we are studying the response for the c, response c with the variation of u, c upon u we are studying. So r infinity that will becomes equals to the 0 in this case of a regulator problem. However, in case of a servo mechanism problem, r infinity that is equals to 1. You have to remember this, because that is we are studying the variation of c upon u. In that c upon u, we are taking the dr upon dt. This is c upon u we are studying, and in this case the dr upon dt that is equals to 0. That is what we are studying, this regulator problem. Change in variation of the set point with respect to time is 0, and that is why r infinity that becomes equals to the 0. So your value of the offset, that is nothing but the difference in the magnitude of the set point and the controlled variable at steady state condition. At steady state condition, that is why we are writing it as the infinity, that is R infinity minus C infinity. So, which comes as the minus 1 upon 1 plus Kc. Taking mod of this offset, you will get a positive value here. So, this is the offset 1 upon 1 plus Kc. So, irrespective of the type of a problem, that is whether it's a servo problem or whether it's a regulator problem, I am getting the same offset for the proportional controller, irrespective of the type of a problem, whether it's a servo problem or whether it's a regulator problem. The offset is there, but the responses are different. Here, the response is 1 upon 1 plus Kc into bracket 1 minus e raised to minus t upon tau dash. And for a servo problem, it is Kc upon 1 plus Kc into 1 minus e raised to minus t upon tau dash. That is what the difference exists in case of a servo mechanism problem and a regulator problem. Similarly, we can have a PD controller for the servo control problem and a PD controller for regulator problem. There, the same way the derivation that can be done, where the response you will get Ct, which is equal to Kc upon 1 plus Kc into bracket 1 minus e raised to minus tau upon tau I upon tau d upon tau 1 e raised to minus t upon tau 1, and where offset that is 1 upon 1 plus Kc for a PD controller. PD controller offset exists. Then for PD controller with a regulator problem, irrespective of the regulator or a servo type of a problem, the offset that exists for proportional controller and for proportional derivative controller. The output response will be 1 upon 1 plus Kc 1 minus e raised to minus t upon tau 1. So output is more or less same as for regulator problem with proportional controller and for PD controller with regulator problem. The same equation you will get in the output. Now the PI controller for servo control problems. So the output response that incorporates a sine term. So that is what a sinusoidal response that is going to get degraded in case of a proportional integral problem, and the offset value that goes to the 0. Similarly, in case of a regulator problem, sine term that is also there, as well as the offset that is 0. Then finally the PID controller, the offset is 0 for servo as well as for regulator problem. That is what we can see this graph for proportional controller, the offset that exists with a certain oscillations. Then for PD controller, the oscillation that are reduced, but the offset that exists. In case of a proportional integral controller, the value of oscillations as well is there and offset is 0. So depending on this type, we are going to have the different applications for that. So proportional controller, where the offset and the oscillations are accepted, that is generally the liquid levels that can be accepted. So that is what the how much offset I can accept. Depending on that, I can keep the value of controller gain Kc. Then in case of a PD controller, the offset is accepted, but oscillations are not accepted. Generally, it is the pressure controlling systems where the variations or fluctuations of the pressure, they are not accepted. Pressure 1 kg ka hai to 1.1 kg, that can be accepted. So I can reduce the set point depending on my process requirement. But variation in the pressure, that is not accepted. Then the PI controller, that is oscillations are accepted, but the offset is not accepted. So in case of a vapor pressure, flow controller, temperature depending on the process conditions, there the PI controller that is used. And finally the PID controller where the offset as well as the oscillations they are not accepted. That is the final temperature controllers and the composition controllers where fluctuations cannot be accepted or the offset cannot be accepted. So this is related to the dynamic behavior of a controller. Now based on this, we are going to discuss the numerical associated with that. So a proportional controller is used for two non-interacting liquid level system. The time constant for the tanks are 1 and 0.5. The value of a gain of a controller is 5. Assume the unity feedback control system. The set point of a control system is given the step change of magnitude 0.4. Determine the offset. Now this problem does not incorporate the block diagram. ये नीचे का पार्ट जो है ये प्रॉब्लम का पार्ट नहीं है, तभी भी ये प्रॉब्लम सॉल्व हो सकता है. That is what is given in the numerical. A proportional controller. One thing.
So the screen is not visible.
Okay. Now okay.
Yes, sir.
A proportional controller is used for two non-interacting liquid level system. The time constant for tanks are 1 and 0.5. The value of a gain of a controller is 5. Assume the unity feedback control system. The set point of a control system is given a step change of magnitude 0.4. Determine the offset. So in this example, this block diagram that is not mentioned, even then you can solve this numerical. Now what is given in the numerical? A proportional controller is given and the two non-interacting liquid level systems that is also given. So what is there? A proportional controller. So I can draw the GC, the proportional controller. Then the transfer function for two non-interacting liquid level systems. The transfer function for 1 upon 1 plus tau s is the transfer function for first system, and 1 upon 1 plus tau 2s is the transfer function for the second system, second tank. As these tanks are non-interacting and the time constants they are given as 1 and 0.5. So time constant 1 upon tau 1s, that is the 1 is the time constant for first system and 0.5 that is the time constant for the second system. So this is the equation for the process incorporating the two non-interacting liquid level systems. Then the value of a gain of a controller that is given as 5. So gain Kc, this is having the value of 5. Then assume the unity feedback control system. So unity feedback, that means the value of B that is equals to the 1. And that is what? The measuring element its transfer function that is not given, a unit feedback control system. So feedback is there, but unit feedback is there. So the set point of a control system is given a step change of magnitude 0.4. A step change of magnitude of 0.4 is given for this, and determine the offset in this case. So writing the overall transfer function for the given figure. So Cs upon Rs, there is no load variable. Only the variation of C and R, only the variation of C with respect to R that can be studied in this numerical. Now C upon R, which is equal to the product of all transfer functions upon 1 plus product of all transfer functions in control loop. That is what Kc, product of all transfer functions between C and R. So Kc into 1 upon S plus 1 into 0.5 S plus 1. That is what? The product of all transfer functions between C and R, and 1 upon 1 plus product of all transfer functions in a control loop. So Cs upon R, for simplification, after that you will get Kc upon 0.5 S square plus 1.5 S plus Kc plus 1, where Kc that is given as the 5. The controller gain, the value of controller gain, that is mentioned as 5. So further simplification, you will get this equation. Now this is a second order equation, S square that is incorporated. So this is a second order equation, and for that you have to simplify it and compare it with the second order transfer function and calculate the value of tau square and 2 phi tau. So from there you can get the value of tau as 0.28 and phi that is 0.43, that is less than 1. This system is underdamped. So the response for the underdamped control system for the second order is Kc into bracket 1 minus e raised to minus phi t upon tau root of 1 minus pi square sine of root of 1 minus pi square t upon tau minus tan inverse of root of 1 minus pi square upon pi. So this is the response I will get. Now I am interested in calculating the value of offset. So at steady state, that means t tending to infinity, what will be the value of C t? So C infinity, that will become equals to the 0.33, because this value that will become equals to the 0 and only remaining is 1. So 0.33 will be the C infinity value, and R infinity is 0.4, that is already mentioned in the numerical, that is the 0.4. The set point of a controller given system is given the step change of magnitude 0.4. This is what a step change that has been mentioned for the magnitude step change, that is nothing but this R infinity. So offset that comes as the 7%. Now the next numerical, that is a proportional controller derivative. A proportional derivative controller is used for the control of the first order system having the time constant tau which is equal to the 30 seconds. The value of a gain of PD controller is Kc which is equal to the 6, and the derivative time tau d which is equal to the 4 seconds. The control system has the first order measuring element for which the time constant is tau 2. If a step of magnitude 0.16 is given to the load variable, determine the value of offset. Now the system is more complicated in this case. That is a PD controller that is provided. The first order system with a time constant T1 as the 30 seconds that is provided. Then the measuring element that is also provided. This measuring element 1 upon tau 2s that is also provided. So the regulator problem, that is Cs upon R, Cs upon U, S, that is what a regulator problem that is mentioned. So 1 upon, that is the product of all transfer functions between C and U. So this is only the one transfer function upon 1 plus product of all transfer functions in a control loop. So transfer function of the first order system upon 1 plus product of all transfer functions in a control system. So after simplification, and comparing it with the second order control system, you will get tau 2 as tau 1 tau 2 upon kc plus 1 as your value of tau, and phi value that comes as 0.85, less than the system is under damped system. So for the under damped system, the Laplace transform that comes out with this thing. So at steady state value, that is t tending to infinity, value of the C infinity, which is equal to 0.16 upon the 7. As this is a regulator problem, the set point does not vary with time. So R infinity that becomes equals to the 0. And so the offset that is become equal to 0.16 upon 7. So any one of you are having any difficulty? This is what we